In this class, I am going to explain about the transient response analysis of transient response analysis of RL circuit. So, transient response analysis of RL circuit. Okay. So, for this, to analyze this RL circuit, transient response analysis, let me consider an RL circuit which was controlled by a switch. So this is an RL circuit, and I am applying a DC voltage source whose value is V. It is R and is L, and this switch is closed at t is equal to 0. There is a time axis, you know that t is equal to 0, 0 minus 0 plus, it is tau, and 5 tau infinity, it is minus infinity. It is a time axis. At t is equal to 0, the switching action is done. What is meant by tau? 5 tau, and why it is called as transient period, I will explain in this class. From here it is a steady state period, it is infinity minus infinity. So let us consider an RL circuit in which the switch is closed at t is equal to 0, and initially the current flowing through the inductor is, let us assume, that is 0, that is I0 is equal to 0 amperes. Initial current flowing through the inductor is 0. That means at t is equal to 0 minus, the current flowing through the inductor is 0. So now in this transient response analysis of RL circuit or RC circuit or RLC circuit, the main things that we are calculating here is the current through the inductor. If it is RL circuit, the current through the inductor. If it is RC circuit, the voltage across the capacitor. And if it is an RLC circuit, the current through the loop we are going to calculate mainly. Now I am going to find this current I of t by applying the KVL for t greater than 0. For t greater than 0, after the switching action is done, this circuit will be like this. The switch is closed now. It is R and this is L, and here it is I0 current will be there. Since I0 current is 0 amperes, so I need not to represent this I0 here, and this is I of t or IL of t. We can also call it as IL of t or I of t, and this is the voltage V. Apply the KVL for this. So it is L, so it is plus and minus, plus and minus, plus and minus. Now if I apply the KVL, it is plus V minus I of t into R minus VL of t, that is L into di of t by dt, L into di of t by dt, that is equal to 0. Now this one, I can rewrite this equation as L into di of t by dt plus R into I of t is equal to V, and this expression I can rewrite as di of t by dt, di of t by dt plus R into R divided by L into I of t, that is equal to V by L. Take this L as common, and if this L is shifted to this side, then it will become V by L here. Now I can rewrite this equation as d plus R by L into I of t is equal to V by L. So it is the first order differential equation, and that too it is a non-homogeneous equation. So the solution for this will have two things. The solution consists of complementary function plus particular integral. Normally this complementary function represents as the transient response. It is the transient response, and this particular integral is steady state response. This transient response can also be called as zero input response, or natural response. This steady state response can also be called as zero state response, or forced response. Okay, these are the different names for the steady state response and and transient responses. So here what I want to explain here is this solution consists complementary function and particular integral. Complementary function is normally represented as transient response, and this particular integral is steady state response. Now complementary function, I can find the complementary function from the homogeneous equation, that is d plus r by L. If I make this is equal to 0, then I can find the value of, I can find this complementary function, and it is I of t. And this I of t, since it is a steady state, it gives the complementary function gives the transient response. This id of t is equal to, so the solution for this one, d plus r by L is equal to 0, d is equal to minus r by L. So this first order differential equation, homogeneous equation, the solution is id of t is equal to k into e power minus r by L into t. So if you know the first order differential equation solutions, you can understand this one. id of t is equal to k into e power minus r by L into t. So it is, let us assume it is equation number 1. And the particular integral I can calculate. Particular integral is nothing but it is a final response or steady state response. Under final states or steady state, this inductor will act as short circuit, we know that. So if I draw that circuit, it is plus and minus, switch is closed, it is R, and this inductor will act as short circuit. So this is the R value, and this is the voltage plus or minus, and this current is nothing but steady state, ISS, steady state current, and this current is nothing but it is a particular integral. So ISS of t is equal to V by R. So this is second equation, and this is the particular integral which gives the steady state response. So final response is this one, steady state response is final response. So if I add this complementary function and particular integral, then I will get the total complete solution for this I of t. So let me write the complete solution here. I of t is equal to complementary function plus particular integral. Complementary function is k into e power minus r by L into t, plus particular integral here is V by R, where k is an arbitrary constant. It is an arbitrary constant, so which can be found from the initial conditions. Initial conditions means t is equal to 0. If I substitute t is equal to 0 here, then I can get the values of this k. Now at t is equal to 0, the current flowing through this RL circuit I am going to find here. So at t is equal to 0 minus, the current flowing through this inductor is IL of 0 minus is 0 amperes. Why? Because initially no current will flow through this. So IL of 0 minus is equal to 0 amperes. That means before switch is on, no supply is connected to this inductance, so no current is flowing. So IL of 0 minus T is equal to 0 minus. T is equal to 0 minus, the current flowing through the inductor is 0 amperes. Now whenever the switch is on, T is equal to 0 plus. T is equal to 0 plus. Just after the switching action is done, the current flowing through the inductor is whatever the current flowing through the inductor at T is equal to 0 minus, same current will flow through the inductor at T is equal to 0 plus also, because the inductor doesn't allow the sudden changes in current. So at T is equal to 0 minus, the current is 0. At T is equal to 0 plus, the current is 0. So there is no change in this current from 0 minus to 0 plus. So at T is equal to 0 also, the current through the inductor is 0. So IL of 0 is nothing but the current flowing through the inductor. That is nothing but I of 0, I of t or IL of t. So here at T is equal to 0, IL of 0 or I of 0. So I of 0 is equal to 0. So this is the initial conditions. Initial condition. That means at T is equal to 0, the current flowing through the inductor is 0. So from that equation, from that initial conditions, I can calculate the value of the K here. So at T is equal to 0, substitute here, I of 0 is equal to K into, so e power something, e power 0. If I substitute T is equal to 0, e power 0 is 1. So 1 plus V by R, already it is present here. So I of 0 value, just now we calculated, this value is 0. I of 0 is 0 here. So now we substitute this 0 here. 0 is equal to K plus V by R. Now K is equal to minus V by R. Now substitute this K value in this expression. So the complete solution I of t is equal to minus V by R into e power minus R by L into t plus V by R. Or V by R, if I take V by R as a common, it is 1 by e 1 minus e power minus R by L into t. So this is I of t. The current flowing through the inductor, it is an expression, important expression. That is, the current flowing through the inductor or in that loop RL circuit is V by R into 1 minus e power minus R by L into t. This can also be solved in another way. What that way here is, you apply this, you use this expression here. What is that? Di by dt plus R by L into I is equal to, or what is that? Variable separable method. That is di by dt, using this expression, di by dt plus what is that? R by L into I of t is equal to V by L. R by L into I of I plus is equal to V by L. So this is the expression, R by L into I is equal to V by L. So I am using this variable separable method here. So what that variable separable method here is, di by dt is equal to V by L minus R by L into I. Di by dt is equal to V minus R into I divided by L. So separate these items and t terms here. So this is an item. So 1 by V minus R into I, that into di is equal to 1 by L into dt. So this is the variable separable method, and apply the integration on both sides of this equation. Then I will get so 1 by V minus Ri into di is equal to integral 1 by L into dt. So to solve this expression, normally we have the integration for this 1 by x dx is equal to log base e x. So this is the expression for this type of integration. But here it is not x here. So what I am doing here is just I am writing v minus r into I is equal to some x. Now what is if I differentiate this equation, 0 minus r into di is equal to dx. Now di is equal to minus 1 by r into dx. So this di and this one substitute here, and see, it is 1 by x, v minus ri is equal to x, dA instead of this dA minus 1 by r into dx is equal to this 1 by l is, it is a constant, it is not a function of time. I can take it out from the integration, so it is 1 by l into integral 1 dt. Now you see, so 1 by x, so it is r is a constant, I can take it out from this integration. So if I take it from this integration, minus 1 by r into 1 by x dx, so the integration for the 1 by x dx is ln x or log x, ln x here. Okay, so we forgot something here. So you see, it is not this v by l, here it is minus 1 by r into ln x. So from this ln x, if I integrate this one, now it is 1 by l into integral 1 dt. If I integrate this one with respect to time dt, then I will get here t. So plus some constant k, because there is no limits here. So if I substitute that limits, we will get this constant k. Now if I want to find this k, I need to use the initial conditions. Before that, substitute the value of x here. What is the value of x? So this is the value of x here, that is minus 1 by r ln means log base e, v minus ri is equal to 1 by l into t plus k here. So to find the value of this arbitrary constant k, use this initial condition. What is that initial conditions? At t is equal to 0, the value of phi here is, just we calculated here, I is equal to, what is it? At t is equal to 0, the value of current I is equal to 0 amperes, is equal to 0, initial conditions. So I is equal to 0. So if I substitute here t is equal to 0, this expression will be minus 1 by r ln v, I is equal to 0 here, it is equal to, this t is equal to 0, so it will become k. So the value of k here is this one, and substitute the value of k in this expression. So this expression will be minus 1 by r into ln v minus ri, that is equal to 1 by l into t plus means it is k value is minus 1 by r into ln v. Now use this one. If I take this minus 1 by r ln v minus ri, if I bring this term to this left side, it is 1 by r plus 1 by r ln v, that is equal to 1 by l into t, and take minus 1 by r as a common here, it is ln v minus ri minus ln v is equal to 1 by l into t. Log a minus log b is equal to log a by b is the formula. So if I apply this formula for this, so it will become minus 1 by r into ln v minus ri divided by v, a by b, that is equal to 1 by l into t. So if I bring this term to the right side of the equation, ln v minus ri divided by v is equal to minus r by l into t. It is minus r by l into t. Now it is log base e. So if I want to find this expression, it is v minus ri divided by v is equal to e power minus r by l into t. What I need to find here is this current I of t. To find this, just cross multiply this one. V minus ri is equal to v into e power minus r by l into t. So if I bring this term to the right side and this term to the left side, then V minus V into e power minus R by L into t is equal to R into Y, and my intention is to find this current. So I of t is equal to 1 by R into V minus V into e power minus R by L into t. If I take V as a common here, so it is V by R into 1 minus e power minus R by L into t. So this is I of t. So it is a complete response for this RL circuit. So like this. So either procedures you can use to find the current that is flowing through the RL circuit loop. Okay. So we find this RL circuit loop current through the inductor I of t, and if you want to draw this, I of t is equal to I of t, or this can also be called as IL of t or I of t, that is equal to V by R into 1 minus e power minus R by L into t. So this R by L, or this can be written as, by taking tau is equal to L by R, where tau is the time constant. I am introducing this time constant here. Time constant for an RL circuit is L by R, time constant. And this current IL of t is equal to V by R into 1 minus e power minus t by tau. I can write like this, it is R by L. So if I write 1 divided by L by R, that is equal to, L by R is nothing but tau. So it is minus e power minus t by tau. I can write this expression like this. Now if I want to find the current flowing through the resistance, the current flowing through the resistance is same as that of the current flowing through the inductance, because these two are connected in series. I want to find the voltage across the resistance. So V R of t is equal to this current IL of t into this resistance offered by that resistor. So IL of t and IL of t both are same here. By multiplying this resistance with this current, I can get the voltage across the resistance. So it is V by R into 1 minus e power minus t by tau into R. This R and this R will get cancelled. So it is V into 1 minus e power minus t by tau. It is VR of t. And if I want to find the voltage across the inductance, so VL of t is equal to L into DIL of t by dt. This is the formula for finding the voltage across the inductance. So L into, if I am able to differentiate this expression here, let us assume it is expression 1, it is expression 2, equation 1, and if I differentiate this equation 1, then I will get V by R with respect to time here. So if I differentiate this 1, it will become 0 minus e power. If I differentiate this e power minus x, then this one is e power minus x. E power minus ax means e power minus ax into minus a. Here it is, a is minus 1 by tau. So here it is V into L by R. This minus and this minus will get cancelled here. 1 by tau. Tau is nothing but L by R. 1 by tau is nothing but R by L into e power minus t by tau. This R, this L will get cancelled. So finally what we got here is V into e power minus t by tau. This is the expression for VL of t. So VL of t, this is VR of t, and this is IL of t, the current flowing through the inductor. These three expressions we need to derive for the transient response analysis of RL circuit. Now I am going to draw the curves with respect to time. This IL of t curve, VR of t curve, VL of t curve. Now I am going to draw IL of t curve with respect to time. With respect to time, how will be the value of this IL of t? IL of t. What is IL of t? IL of t is equal to V by R into 1 minus e power minus t by tau. This is the expression for finding this current flowing through the inductor in an RL circuit, RL series circuit. Now you see, if time t is equal to 0, it is the point at t is equal to 0. If I substitute t is equal to 0 here, e power 0 is 1. So 1 minus 1 is 0. So this total value is 0. That means IL of 0. It means at time t is equal to 0, the current will start from 0. Right. So this expression at t is equal to 0. At t is equal to 0, IL of 0 is equal to 0. Now at t is equal to infinity, t is equal to infinity, what is the value of e power minus infinity is 1 by e power infinity. 1 by e power infinity is nothing but 1 by infinity. 1 by infinity is nothing but 0. So the total value will be 0 here for t is equal to infinity. So it is v by r into 1 minus 0 is v by r. So IL of infinity is v by r. So this is the initial value and it is the final value. Let us take that final value as v by r. So this is v by r here. It is v by r. Okay. Now initially it is at 0. Initially it is at 0. It is at 0, and finally at t is equal to infinity it reaches to v by r. So these 2 points we got here. In between these 2 points, I am interested at t is equal to some tau. At t is equal to some tau, what is the value of this IL of t here? So IL of tau is v by r into 1 minus e power tau by tau, that is equal to e power minus 1. So e power minus 1 value is v by r into 1 minus e power minus 1 value is 0.368. So it is IL of tau. So IL of tau is equal to v by r into 1 minus 0.368 is nothing but 0.632. That means, so at one time constants it is reaches to 0.632 v by r, IL of tau. Now I am defining this time constant here. That means it is 63.2% of, this is the final value, v by r is the final value, 63.2% of final value, that is v by r. That means at one time constants, let me take here, it is the tau here. So at one time constants, the value of this IL of t is nothing, is 0.632 v by r. It is 0.632 v by r at one time constants. Now at 5 tau time constants, I am taking only this tau and 5 tau. So the reason behind that I will explain after completion of this explanation. Now at t is equal to 5 tau, IL of 5 tau is equal to this v by r into 1 minus e power, instead of t I am replacing with 5 tau, it is e power minus 5. So it is if I solve this 0.993 into v by r. So IL of t is nothing but 0.993 v by r. So let us take this, that is approximately, it reaches to this 0.993 means it is approximately 1 only. So v by r, that means it reaches to its final value. So if I draw these graphs, this point and this point, then this graph will be like this. It is somewhere it touches to this v by r line and t is equal to infinity. So it is this is the expression, sorry, it is the graph for this current IL of t in an RL circuit, and this point is tau. This is the tau. So tau, time constant can be defined as, it is the time required for the response to complete 63.2% of its final value. So 60.2% of its final value. It is the time. So time constant we can define like this, and the time constant for an RL circuit is L by R. This is important. Next, phi tau time constants. So this time is nothing but phi tau. So this response is nothing but transient response, as we already discussed, steady state response, and our analysis is in between this 0 to phi tau only. So this period is called as transient period. Okay. Now if I want to draw the curves for this VR of t and for this VL of t, so first let me draw this VR of t curve here. Here I am drawing VR of t and also VL of t, both the curves in one graph. I am going to draw here, and you see VR of t is equal to V into 1 minus e power minus t by tau. Only the change between this L of t and this VR of t is there is V by R, here is only V, there is no R here. So here the final value is V by R, but here the final value is only V here. Final value is V. Why? Because at t is equal to 0, the value of VR of t is, VR of 0 is, if I substitute e power 0, 1 minus 1, that is 0. So it is 0. That means it will start from here. The same curve, it will follows the same curve as the current curve follows. Okay. Because it is the same expression, just the magnitude changes here. Instead of V by R here, it is V now. So it is phi tau, let us assume it is tau, phi tau. Then this expression will be like this only. Okay, this is the curve, it is VR of t. Now VL of t is equal to, what is VL of t here? VL of t is V into e power minus t by tau here. V into e power minus t by tau. Right. So here whenever t is equal to 0, if I substitute t is equal to 0 here, e power 0, that is 1 into V. So it will start from V itself. At t is equal to 0, VL of 0 is equal to V. At t is equal to infinity, so it is e power minus infinity, 1 by e power infinity, 1 by infinity. So 1 by something divided by infinity is equal to 0. 0 into V is 0. So VL of infinity is 0 volts. That means it is a reverse, it follows the reverse. And at t is equal to phi tau, VL of phi tau is equal to e power minus 5. It is almost 0.0064 something. So approximately it is 0. So it follows like this. This curve follows like this. So it is VL of t. So these are the things that you need to write in the examination for IL of t, and this is the expression for IL of t, VR of t, VL of t. After finding the expression for IL of t, VR of t and VL of t, draw these curves here. This is for IL of t, these curves are for VR of t and VL of t. Next we will solve some of the problems on this RL circuit concept. So problems on RL circuit. as we already discussed in this, we are going to find I of t or IL of t or VL of t, like that. Okay, mainly we will focus to find these things, IL of t or I of t. So here this is one problem, you can understand this. So for this network shown in figure, this is the problem. For the network shown in figure, steady state is reached with the switch is closed. That means initially the switch is closed, so at the time the steady state is reached. That means from minus infinity to 0, the switch is closed and the steady state condition is reached. The switch is opened at t is equal to 0. So at t is equal to 0, the switch is open. Obtain the expression for IL of t and VL of t. So this is the current flowing through the inductor IL of t and voltage across the current VL of t. These two things we need to find. This is the network. In this network, initially the switch is closed, that is from minus infinity to 0. At t is equal to 0, the switch is open. Now we need to find this IL of t and VL of t expressions. So to solve this type of problems, what we need to do here is, first we need to draw the circuit at t is equal to 0 minus, so that we can find the values of IL of 0 minus, or if there is a capacitance, we can find the value of VC of 0 minus. After finding the values of IL of 0 minus and IL of 0 plus also is same as that of the IL of 0 minus, because the inductor doesn't allow the sudden changes in current. So after finding this IL of 0 plus is equal to IL of 0 minus is equal to I0, that is equal to IL of 0, next step is we need to draw the circuit for t greater than 0. After drawing the circuit for t greater than 0, write down the integral differential equations by applying KVL or KCL. So let me expand this problem so that you can understand. So first, at t is equal to 0, at t is equal to 0 minus, t is equal to 0 minus, the switch is under open position, the switch is under closed position, the switch is closed position. So now this will be like this. This is the inductance value. So under steady state condition, this inductance will act as short circuit. This inductance will act as a short circuit, because it is 0, 0 minus, 0 plus, it is infinity, it is minus infinity. Okay, time axis. At t is equal to 0, the switching action is done. That means the switch is open. So from minus infinity to 0, a switch is connected. That means under this position, under this time, the circuit is under steady state condition, steady state. So under steady state condition, if the inductor is there, then it should be short circuit. If the capacitor is there, that should be open circuited. Now this current IL of t or IL of 0 minus, and this is 100 ohms and this is 3000 ohms. 3000 ohms, it is 15 volts. So even this resistor is connected across this short circuit, no current will flow through this 3000 ohms, because the current always prefer to flow through low resistance path. So the resistance offered by this short circuit is R is equal to 0. So there is no current flowing through this, there is no voltage drop across this one, no power absorption for this resistor. So I can remove this resistor here, or otherwise if any short circuit is connected across any resistor, then it will also become a short circuit. So this circuit will become like this. It is a short circuit for the inductor. So it is IL of 0 minus, it is the resistance 100 ohms, it is 15 volts. Now IL of 0 minus, the value of IL of 0 minus here is, it is 15 divided by 100, it is 0.15 amperes, 0.15 amperes. Now we know that at t is equal to 0 plus, the current flowing through the inductor is same as that of the current flowing through the inductor at t is equal to 0 plus, because the inductor doesn't allow the sudden changes in current. So I L of 0 plus is equal to I L of 0 minus is equal to, it is initial current I 0. So I 0 is equal to 0.15 amperes. If 0.15 amperes at this point and at this point also, at this point also this is 0.15 because there is no change in current. So I L of 0 is also 0.15 amperes. Okay, we got this expression. Next, 40 greater than 0. 40 greater than 0, this circuit, I'm going to draw the circuit here for this. Now the switch is open. The switch is open here because t is equal to 0, the switch is open here. So 40 greater than 0, the switch is open. Now this circuit will become like this. So this is the inductance and this is the current flowing through that inductance. We can replace that inductor circuit like this. At t for t greater than 0, the circuit will be like this. This L value is 90 millihenry, and this is L of t. This current that is flowing through this is I of t. Sorry, okay, we don't want about this L of t. Same current I of t, and it is 3000 ohms. And we don't want about this 100 ohms and this 15 volts because it is open circuited. It is no way connected to this circuit. So only we need to consider this circuit only. Now it is plus and minus. This is plus and minus. Now apply the KVL for this. It is minus 3000 into, it is I of t. It is minus. It is also minus VL of t is equal to 0. VL of t is nothing but VL of t is equal to, or VL of t, what is the value of VL of t? Minus 3000 into L of t minus L into dL of t by dt. L value is 90 into 10 power minus 3 into dIL of t by dt is equal to 0. Now this can be written as, if I here I can rewrite this expression like this: 90 into 10 power minus 3 into dIL of t by dt plus 3000 into IL of t is equal to 0. Take this 90 into 10 power minus 3 as a common and bring this term to the right side of that equation. Then I will get dIL of t by dt plus 3000 divided by 90 into 10 power minus 3 into IL of t is equal to 0. So dIL of t by dt plus 3000 divided by 90 into 10 power 3 into IL of t is equal to 0. This one 300s, 3 3s. So it is 33.33. So dIL of t by dt plus 33.33 into 10 power 3 into IL of t is equal to 0. So it is a first order differential equation, first order homogeneous differential equation. So for this type of equations, the solution will be, suppose it is di by dt plus p into I is equal to 0. For this type of problem, so the solution will be I of t is equal to k into e power minus pt dt, k into e power minus pt, and k value is an arbitrary constant. K is an arbitrary constant which can be obtained by substituting the value of t is equal to 0. That means from the initial conditions, I can get the value of this k. Suppose if this differential equation is non-homogeneous equation, that means if it is di by dt plus pi is equal to q. So for this type of expressions, the I of t can be calculated as k into e power minus pt. I of t is equal to k into e power minus pt plus e power minus pt into integral q into e power pt dt. So these are important for solving the problems. Okay, so this is the solution we can find for homogeneous non-homogeneous equations. For homogeneous equations, this is how we can find. Next, so for this type of problem where the p value here is p is equal to 33.33 into 10 power 3. So now IL of t is equal to k into e power minus pt, that is equal to k into e power minus 33.33 into 10 power 3 into t. So it is IL of t, and this k value we can find from the initial conditions. What is that initial conditions? So at t is equal to 0, the value of the current that is flowing through the inductor, we already calculated. What is the value of the inductor that is flowing through this inductor at t is equal to 0? 0.15 amperes. 0.15 amperes. So it is 0.15 amperes. Now substitute in this expression. So L of 0 is equal to 0.15, that is equal to k into e power, if t is equal to 0, total 1 will become 0, e power 0 is 1, so k into 1, so k value is 0.15. Substitute in this expression. So L of t is equal to 0.15 into e power minus 33.33 into 10 power 3 t. So this is L of t. So we find the value of L of t. Next thing here is VL of t. We need to find the value of VL of t, and it is for t greater than 0. That means we can find the current through the inductor at any time after t greater than, after time 0, after switching action 0. We can find at t is equal to infinity, we can find at t is equal to 0, we can find at t is equal to 3 seconds, 4 seconds, 20 seconds, at whatever the time may be, we can find using this expression. Next, VL of t. As we know that the formula for VL of t is equal to L into dL of t by dt. Just we need to differentiate, and L value here is 90 millihenry, 90 into 10 power minus 3 to dAl of t by dt. If I differentiate this expression, so it is e power minus ax, it is 33.33 into 10 power 3t into minus a, that is minus 33.33 into 10 power 3. So now this expression, if I find this expression, 33.33 means it is 100 divided by, I think it is 3000 divided by 90. We already calculated this. It is this one. 3000 divided by 90 is 33.33. So it is this value is 3000 divided by 90, and this 90 and this 90 will get cancelled here. So it is 0.15 into 3000. So it is 15 trees.